Okay, now let's start proving the Hurwitz theorem. First observation is that without loss of generality, we may assume the irrational number alpha is greater than 0. This is because the inequality we want to establish is something like this. And because of the absolute value here, it doesn't really matter whether alpha is positive or negative. It doesn't matter whether alpha is positive or negative. We can always flip the sign of p correspondingly. Now suppose a over b and c over d with alpha squeezed between them are the two ratios adjacent to alpha in the breakout series B-span. Here is our goal. Our goal is to use the information of those numbers A, B, C, D to produce some rational number p over q such that we have alpha minus p over q less than 1 over square root of 5 times q squared. And actually by produce, we do not actually mean we want to construct explicitly something. Alternatively, it suffices to prove the existence of such a thing, which may not necessarily have a very concrete formula. And that's the idea of the proof. And now we will start by studying the relations between alpha and those numbers A, B, C, D. There are several cases to consider. First, if b squared plus b squared minus bd times square root of 5 plus d squared is greater than 0. And hopefully this reminds you of something we just did above in here. Under this case, we claim that either alpha minus a over b is less than b squared times square root of 5, or c over d minus alpha is less than the square of d times square root of 5. Now let's check this claim. First, suppose we have the reversed inequality. The trick is that you add them up. What you get on the right hand side is 1 over square root of 5 times 1 over b squared times plus 1 over d squared. And on the left, what you get, notice alpha cancelled out, c over d minus a over b. Okay, now, does this remind you of anything? Think for a while. We have seen this before. This is actually a lemma we just proved above. Specifically, it is this lemma. Exactly the same. And by the lemma we proved above, the left-hand side is equal to 1 over b times d. And this gives you this inequality, which can be simplified into square root of 5 times bd greater than b squared plus d squared. So what is this? This is a contradiction. So we verified this claim. Okay, now we have got some partial result about the thing we want to prove. That's good. That's a good beginning. And now let's move on. Now the second case is if b squared minus bd times square root of 5 plus d squared is less than 0. Remember in our first case, this guy is assumed to be greater than 0. Okay, now how do we deal with this case? In mathematics, there's a general philosophy. If you have several cases to consider, and you have solved some of those cases, what can you do with the rest? In general, you are not going to always start from the scratch. What you should first think about is that whether you can reduce the rest cases into the cases you already know. And this is the philosophy that we are going to follow in here. We are going to reduce this second case to the first case. So with this inequality, if we divide both sides by d squared, we will get b squared over d squared minus square root of 5 times b over d plus 1, which is strictly less than 0. And you do the factorization of this, you will get b over d minus square root of 5 minus 1 over 2 times b over d minus square root of 5 plus 1 divided by 2. This product is less than 0. Then we have b over d is strictly greater than the root of 5 minus 1 divided by 2 less than root of 5 plus 1 divided by 2. Okay, now I tell you, with this information, you can reduce the second case to our first one. To our first case. And to make this reduction, you need to use one of the observations we made earlier. I'll let you think about it on your own, but I will tell you the answer anyway. So you might want to pause this video for a while. Okay, now I will tell you the answer. The observation I meant is this one. This says you can manipulate the relations between the golden ratio and the rationals by adding 1. Another trick is the following. If you add 1 to this inequality, you get 5 plus 1 divided by 2 is less than b over d plus 1, which is equal to the b plus d divided by d. And what does this tell you? This tells you that b plus d divided by d minus square root of 5 minus 1 times b plus d divided by d minus square root of 5 plus 1 divided by 2 is greater than 0 because both of them are greater than 0. But this gives you another homogeneous inequality, which is b plus d squared minus square root of 5 times b plus d times d plus d squared greater than 0. And now, one more observation. Notice that in this homogeneous inequality, the positions of b and d are equivalent, which means you can always flip b and d. So, symmetric to this inequality, we also have the other one by flipping b and d. What I mean is that you have d plus b squared minus square root of 5 d plus b times b plus b squared greater than 0. And now do you see how this reduces to our first case? Yes, the format of this looks exactly like the format of the first case. You just replaced one of the letters by the sum of two letters. That is the only thing we changed. Okay, that's a big progress. And now we want to study the relation between this and alpha as we did in the case 1. There will be two cases. First, if alpha, remember that alpha is assumed to lie between a over b and c over d. Now, if alpha is smaller, which means that alpha is greater or equal to a over b but less than a plus c divided by b plus d, then from the inequality b plus d squared minus b plus d b times square root of 5 plus b squared greater than 0, and with b plus d replacing d, a plus c replacing c. In the case 1, remember in case 1, we proved the following claim, which gives the estimate for a in terms of the rational numbers. And here, by making some trivial replacement, we conclude the similar thing, that either a minus a divided by b is less than 1 over square root of 5 times b squared, or a plus c divided by b plus d minus alpha is less than 1 over square root of 5 times b plus d squared. And although it is trivial, I should add that the left-hand side is always greater than 0. And now, in the second case, if alpha is greater than a plus c divided by b plus d, but less than a over b, do you think you can conclude something like this? I believe you can. I would like you to think for a while on your own, but I will tell you the answer anyway. So here's the change that you want to make. So instead of b here, you want to put d. And instead of d here, you want to put b. And instead of c here, you want to put a. And the conclusion we can get from this situation is that either alpha minus a plus c divided by b plus d is less than 1 over b plus d squared times square root of 5, or c divided by d minus alpha is less than 1 over d squared times square root of 5. And of course, left-hand sides are greater than 0. And now we have completed those two cases, and I believe you can summarize our proof so far and find the conclusion we want. You want to pause the video and think on your own for a while. To summarize what we have got, we've got 6 inequalities. 1, 2, 3, 4, 5, and 6. 6 inequalities. And the conclusion that we can get from those 6 inequalities is that one of the following 3 inequalities holds. The first one is the absolute value of alpha minus a divided by b is less than 1 over square root times b squared. And the second one is alpha minus a plus c divided by b plus d is less than 1 over square root of 5 times b plus d squared. And third one is alpha minus c divided by d less than 1 over square root of 5 times d squared. And this tells us that for each n, there exists a pair p over q that is either in b sub n or b sub n plus 1, as in the Broca series, such that the square root, the absolute value of alpha minus p over q is less than 1 over square root of 5 times q squared. And this is the inequality that we want to get. But wait, it is not done yet. Remember the Hurwitz theorem requires that there are infinitely many rational numbers. And here we just got one of them. How do we get infinitely many? So the question will be how to get infinitely many pairs p over q satisfying, let's call this star. This follows from the structure of the Broca series. So recall this is a table for the Broca series, and our alpha always lies between two adjacent pairs in the Broca series in each level. As the level gets bigger, the Broca series will get finer and finer. And because alpha is irrational number, as you keep dividing, you can always squeeze alpha between two new pairs eventually. Since alpha cannot be equal to any number in the Broca series, it cannot belong to the Broca series. That is why you can produce infinite many pairs satisfying the star inequality. To make my argument more precise, let me make the following observation. Suppose alpha is a positive irrational number squeezed between two adjacent pairs in the Broca series A, B, C, D. Then, for sufficiently large integer m, we have alpha is squeezed between ma times ma plus c over mb plus d, and a plus mc over b plus md. This observation is very easy to verify, and it tells us as this n become bigger and bigger, there will always be new pairs squeezing alpha. The alpha will not stick with the same pairs all the time. You can always get new pairs, and the result you proved here will change with n. So those A, B, C, D will change with n, so that you can get infinite many P over Qs satisfying this inequality.